In this video, we're going to look at modeling exponential decay, such as what might happen with radioactive decay or medicinal dosage. One of the most classical examples of exponential decay is that of radioactive decay, in which a mass of a radioactive element decreases over time. The formula for this is exactly the same as for exponential growth. Here we use A instead of P to represent the amount of the substance instead of P, which stood for population. And we have A of T equals A sub 0 times A to the T. And all of these represent the same, essentially the same quantities as for exponential growth. A of T is the amount remaining after time T. A sub 0 is the amount at time T equals 0, or the initial amount. And the value of lowercase a is called the decay rate. And with a decay problem, this is going to be a value of a somewhere between 0 and 1. Recall that for an exponential growth problem, a would be bigger than 1, but for exponential decay, we should expect a to be somewhere between 0 and 1. One commonly used term related to radioactive decay is that of half-life. And this term essentially defines itself. It is the time that it takes for half of the substance to decay. So for example, if we have 100 grams of some radioactive substance, and that substance has a half-life of 2 hours, if we return 2 hours from now, we'll see that there are exactly 50 grams remaining. And that's half of the 100 grams that we started with. If we come back 2 hours after that, we would see that there are only 25 grams left, which is half of 50. So let's start by considering this example. Here we have a scientist with 12 grams of palladium-100, which is known to have a half-life of 4 days. And we'd like to know how long it will be until there are only 4 grams of that 12-gram sample remaining. So we'll start with our standard exponential decay model. A of t equals a sub 0 equals a to the t. Here we are told that a sub 0 is going to be 12. And we're also told that a of 4 is going to equal 6. And while this is not directly given to us, the half-life information tells us that this is the case. It tells us that after 4 days, there'll be half of the substance remaining, and half of 12 is 6. So if we start with 12 grams, if a sub 0 is equal to 12, then a of 4 will equal half of that, which is 6. We can substitute these numbers into our model, and we obtain 6 equals 12 times a to the 4th power. We're going to solve for a by first dividing both sides by 12. When we divide by 12, we get 6 over 12, which is just 1/2. Right? And this is actually not surprising. Because we chose 6 because it was half of 12. So with half-life, we will always end up with 1/2 on the one side, like in this case. And that is equal to a to the 4th. To solve for a, we raise both sides to the 1/4 power. So 1/2 raised to the 1/4 power. And this is approximately 0.8409. Right, so that's rounded to 4 decimal places, 0.8409. And this means that our model for our exponential decay is going to be 12 times 0.8409 to the t. And now we can use this model to answer the question. We want to know how long it will take for there to be only 4 grams of this substance remaining. And so we'll let P of t equal to 4 and solve this equation for t. Okay, so we will replace the a of t with 4, and that's equal to 12 times 0.8409 to the t power. We'll divide both sides by 12. On the left side here, we'll end up with 4 over 12, which is 1/3. And that'll equal 0.8409 to the t. In order to get t out of the exponent, we need to take a logarithm. And here we'll take natural log. We can also take common log if you prefer. But when we do this, This will allow us to bring the t down in front of the logarithm. So this will be t times natural log 0.8409. Okay. And then to solve for t, we simply divide by that natural log of our decay rate. So we have the natural log of 1/3 divided by the natural log of 0.8409. When we go to a calculator, we see that this equates to about 6.34 days. So it's going to take a little over 6 days for this 12-gram sample of palladium 100 to decay down to 4 grams. For another example, let's suppose we started with 750 grams of a radioactive substance, and after 10 hours, we have only 625 grams remaining. Here we want to answer 2 questions about this scenario. We'd like to know how much of the substance remains after 24 hours, and we'd also like to determine the half-life of the substance. Just like in the previous example, the first step is to develop an exponential model that gives us the amount of this substance after t hours. This is something that is done very similar to how it was done in the previous example, and so it's going to be left to you to try this on your own. The correct model, though, should be A of t equals 750 times 0.9819 raised to the t power. Right? This is the model that we're going to use to answer the 2 questions posed here. For our first question, we're looking for the amount of the substance remaining after 24 hours. In other words, we're looking for the value of A of 24. In order to compute A of 24, we're simply going to replace t in our model with the number 24. So we have 750 times 0.9819 raised to the 24th power. And we can use a calculator to compute this value, and it'll be approximately 483.81. This is in grams. So after 24 hours, approximately 483, almost 484 grams of this substance will remain. In part B, we're asked to find the half-life of the substance. So what we want to do is we want to find the value of t when A of t, the amount at time t, is equal to half of 750. Right, which is 375. So we want to find the value of t where A of t is equal to 375. And so we can substitute 375 into our formula and solve for t. So we obtain the equation 375 equals 750 times 0.9819 to the t, and we want to solve this equation for t. To do that, we first divide both sides by 750, and we will get 1/2 on the left side. This actually makes complete sense because the 375 was determined by taking half of 750. And so that'll equal 0.9819 raised to the t. To get the t out of the exponent, we're going to take logarithms of both sides. And apply the power rule for logarithms, bringing the t out front of that logarithm. So it's t times natural log 0.9819. Right, to solve for t, then, we just simply divide by that logarithm. So we end up with logarithm of 1/2, natural log of 1/2, divided by the natural log of 0.9819. And again, using a calculator here at the very end, we see that this is 37.95 hours. So it takes essentially 38 hours for this particular substance to reach half of its starting mass. And so the half-life is about 38 hours. Here we take a look at one more example of an exponential decay model that is not a radioactive decay problem. In this example, a patient is given 50 milligrams of some medication, And it is known that the amount remaining in the bloodstream after T hours is exponential. The medication is ineffective if if less than 10 milligrams is in the bloodstream at a given time. So if there is 40 milligrams remaining after 2 hours, we'd like to know how long it will be until the medicine needs to be administered again. In other words, we want to know when will the amount of medicine in the bloodstream be 10 milligrams. At that point, since the medication is ineffective for less dosage, we would need to re-administer this particular medicine. And so, as always, we're going to set up an exponential decay model that models this situation, the amount of the medication remaining in the bloodstream at a given time t, and then we're going to use it to answer this particular question. So we know we're looking for an exponential model of the form a of t equals a sub 0 a to the t. We are given the initial dosage. In this case, that's a sub 0 equals 50 milligrams. And we're given the fact that after 2 hours, there are 40 milligrams left in the bloodstream. So a of 2 would equal to 40. We can now substitute these values into our model and solve for the decay rate A. So when we substitute, we will get 40 equals 50 times A squared. If we divide both sides by 50, on the left side we get 40 divided by 50, or 4/5, and that's equal to A squared. To find the value of A, we can simply take the square root of 4/5, or we can take the 1/2 power. Either option will work. They would, of course, do the same thing. And this is approximately 0.8944. So our decay rate is 0.8944. So our model that we're going to use to answer our question is a of t equals 50 times 0.8944 to the t power. Right. What we want is we want to find the value of t where a of t is equal to 10. This will give us our time after the initial dose in which we need to re-administer the medicine. And so we'll substitute 10 in to this equation for a of t and solve for t. So we obtain 10 equals 50, 0.8944 raised to the t power. We divide both sides by 50, and we'll end up with 10 over 50, or 1/5. Will be 0.8944 to the t. And as we have in all of our other examples, we will now take natural log and solve for t. The key here is that there's really nothing different about this example from the radioactive decay problem other than the application itself. The actual mathematics here is exactly the same. And once we have t out of the exponent, we can simply divide by the logarithm it's being multiplied by to find the value of t. So we get natural log of 1/5 divided by the natural log of 0.8944. And if we use a calculator to compute this value, we get approximately 14.42 hours. This tells us that about 14.5 hours after the medicine is initially given, that it will need to be redistributed to maintain a threshold of more than 10 milligrams in the bloodstream.